My dear students, Assalamu alaikum and adab. In this lecture, we will discuss the bending stresses developed in beams, how these stresses are developed, how we evaluate, how we analyze a beam for bending stresses, what is the effect of these bending stresses in a beam. So first of all, we have a look at bending stresses. So it is a type of stress which is developed due to the bending effect. Now, if we consider a beam, say we consider a beam simply supported span L loaded with a certain UDL of intensity W per meter. This is a beam. Now, the effect of this load is that it will produce two things. It will produce the shear force in a beam. Shear force is the unbalanced force which will be acting on the beam along the length of the beam. Unbalanced force on either side of the section. This is the variation. So this may be W into L by 2. This is the shear force diagram. One more effect will be the bending effect. This load will produce bending moment also. This bending moment with a maximum value of WL square by 8 here. This will be the bending moment diagram which will create a tendency of bending. It will try to bend the beam. So the beam, if we consider this bending effect, the beam will develop certain internal stresses to resist this bending. Such internal stresses which resist this bending developed because of the load acting on the beam are known as bending stresses sigma B. So these stresses are the internal stresses developed across the cross section of the beam because of the action of load which produces bending in the beam. Now this bending stress is then of two types. It may be bending compressive stress or it may be bending tensile stress. So depending upon the type of stresses, they are classified as bending compressive or bending tensile stresses. Now, if the same beam we analyze, this is the same simply supported beam acted upon by certain load. When this beam bends, its plastic curve will be something like this. It will bend like this. Now, when it bends like this, these fibers are stretched, so they are under tension. These fibers are compressed, so they are under compression. The stresses which will develop across this cross section will be bending compressive stresses at the top, bending tensile stresses at the bottom. So, in a simply supported beam, the nature of change will be from bending compressive stresses at the top to bending tensile stresses at the bottom. There will be a level where this compression and compressive stresses will change over to tensile stresses, and this level is at the CG. This is known as the neutral axis. So there will be no stress at the neutral axis. There will be a changeover of the stress, of the nature of stress at the neutral axis. Say we have a cantilever beam now. This is a cantilever beam of span L, loaded with the UDL W per meter. When the beam will bend, when this type of beam will bend, it will have an elastic curve like this. See here, these fibers are now stretched, so we will have bending tensile stresses at the top. These fibers will be compressed, so we will have bending compressive stresses at the bottom. So the nature is different than that of the simply supported beam. It will depend upon the type of the beam where these compressive stresses will be developed and where the bending tensile stresses will be developed. Same thing here also, we will have a neutral axis at the CG. There will be no stress at the neutral axis. So these are bending stresses. Now we have a case of pure bending, what we call simple or pure bending. Simple or pure bending. This simple or pure bending is bending which takes place where there is no shear stress or there is no shear force. So a bending stress developed in an area where there is no shear force is called case of pure or simple bending. Say for example, this is an overhanging beam loaded with point load W here and W here. These are the overhangs A. This is span L. Overhang A. Okay. When we evaluate it for shear force, the shear force diagram will be something like this. This load will be W. It will come 0 here. 0 will continue up to the next support, and again W here. So W, W, 0 in between. No shear force here. When we will go for the bending moment diagram, this will be W into A. Here also W into A. And this will be W into A. This will be the bending moment diagram. This is the shear force diagram. Now, this is the case of pure bending. Here, see, there is no shear force in this particular area. It's only bending moment. So, the bending stresses will correspond to pure bending. But this may not be the case always. We may not have zero shear force at all the locations. But, say, a simply supported beam loaded with UDL will have a shear force diagram something like this. Shear force is 0 at the center. Bending moment will be maximum here. This bending moment will be WL square by 8 at the center where shear force is 0. So bending moment is always maximum where shear force is 0. So we calculate the bending stresses corresponding to maximum bending stress, bending moment, and this bending moment is going to be maximum where shear force is 0. So it complies with the theory of simple or pure bending. So before we analyze the beam for this bending stress, we see certain assumptions. There are certain assumptions within which this bending stress or this bending equation will be valid for. The section, first one is that the section which is plane, before the bending takes place, it will continue to be plane after bending. That is, there will be no change in its cross-sectional dimensions. The material is homogeneous and isotropic. There is no change in its properties along the direction. The section is uniform. Cross-section is uniform throughout the length of the member. The section obeys the Hooke's law. It obeys the Hooke's law, that is, the stress will be proportional to the strain. It will be stressed up to elastic limit only. Then we have the radius of curvature. This radius of curvature along which the beam bends, this radius of curvature is quite large before the bending takes place. The member is made up of certain layers. It's made up of certain layers which are free to contract and expand. They are free to contract and expand. Then we have seventh, that there is no resultant pull or push. There is no resultant push or pull on the member. And the modulus of elasticity. Modulus of elasticity. This E is constant. So this bending equation, what we will derive, will be valid within all these parameters, within all these assumptions only. Now with this concept of bending stress and the assumptions made, we come to the equation for analysis of bending stresses, that is the bending equation. Bending equation. We analyze, in other terms, we analyze the bending stress developed in a member using this bending equation. Consider this member. This is a beam of certain length L. At the center, this is the CG, PQ. This is the neutral axis of the beam where the stresses are going to be 0. We analyze a small strip AB located at a distance y from the neutral axis. Now, when bending moment occurs, when bending moment is developed, the beam may bend like this. Beam has a tendency to bend like this. When it bends, a certain radius of curvature is developed. P dash Q dash will become the neutral axis. A dash B dash is the strip which was under analysis. Area of the strip is delta A. Then we have change in the length. Because of this bending, certain change in the strip which is under analysis. Change in the length is the original length minus the changed length A dash B dash. This is the change in length delta. And strain. is change in length, AB minus A dash B dash, change in the length divided by the original length. Okay, this is strain. Strain, we have stress by strain is the modulus of elasticity E. So this strain I can write stress divided by modulus of elasticity E. And out of this we can write that E strain is equal to stress divided by modulus of elasticity, which is further equal to AB minus A dash B dash, change in the length divided by the original length AB. Okay. This is one of the equation. Now come to this figure. From this figure we have, since the R is large, we will take OP dash Q dash, take O P dash Q dash, we take it similar to O A dash B dash. When this we consider similar, out of this what we will have? We will have A dash B dash divided by P and Q dash shall be equal to, in terms of R is up to this point, up to the neutral axis, up to this point it will be R minus Y. So R minus Y by R. This we can get out of the similarity of the triangles. Now if I subtract it from 1 on either side, what we will have? This will become P dash Q dash minus A dash B dash divided by P dash Q dash. This will become R minus R plus Y by R. R and R will go. So this will be Y by R only. Okay, at P dash Q dash, this is, before bending it was PQ, or PQ is the same as AB. So instead of P dash Q dash, I can write AB. I can write AB. So I will get AB minus A dash B dash divided by, again, AB in place of P dash Q dash shall be equal to Y by R. Okay, but this term is already equal to this stress divided by modulus of elasticity. So we will have stress divided by modulus of elasticity is equal to Y by R. Or we will have stress divided by this distance Y shall be equal to E by R. So this is what we get. So we have sigma by this Y, sigma is the bending stress, Y is the fiber distance, is equal to modulus of elasticity divided by R, radius of curvature. So this is one equation. So I write it here. We have sigma bending by Y equal to E upon R. Okay, this is one part of the equation. Then moving ahead, we have this moment on the strip. On the strip, bending moment. Moment is what? Moment is force into some distance. Say some force multiplied by distance. Now force is further equal to some stress into area into distance. Okay? Stress is area of the member is, of the strip is delta A. Stress, out of this equation, if I take sigma, that will be equal to E upon R into Y. Area is delta A and distance is this Y. Okay, this will be moment. If I calculate moment for the entire section, I integrate this. I integrate it. Here also, this E by R is a constant. So I will have Y square into delta A. Okay. Integrating this, we will have moment M. Bending moment or moment of resistance for the section. E by R is a constant. Y square delta A. This is area into distance, again into distance. That is second moment of area. Second moment of area is nothing but moment of inertia. So I can write inertia in place of this integration of Y square divided by into delta A. Out of this now, I will get M upon I. M upon I is also equal to E by R. This will be second equation. Okay. So out of the two equations, if we combine these two equations, we will have M upon I is equal to sigma bending divided by y, which is again equal to E by R. This equation is known as the bending equation. Out of this, M is the bending moment or the moment of resistance of the section, I is the moment of inertia of the section, bending stress sigma B, Y is the distance of the fiber from the neutral axis, E is the modulus of elasticity, and R is the radius of curvature. This equation is known as bending equation, and bending stress is calculated out of this equation. From the help of this equation, we calculate bending stress along the cross section of the beam. Okay, now how this is calculated and what is its variation? That variation we call bending stress diagram. Bending stress diagram. Variation of bending stress along the depth of beam is the bending stress diagram. Say for example, if I take the example of a cantilever beam, say this is a cantilever beam. Okay, it has got a span L. It has got certain UDL of W per meter intensity. The cross section of beam is a rectangular beam of size B by T. Okay. Now I have to see how this bending stress will vary along the depth of the beam. First of all, we find out the bending moment diagram, how the variation of bending moment diagram takes place. So bending moment is maximum here, that is equal to WL square by 8. This is the maximum bending moment. This is bending moment diagram. Okay. So we have the value M. Other values, see our bending equation says that M upon I is equal to bending stress, either compressive or tensile, divided by Y. Okay. Y is the distance at which fiber we are calculating the distance. So Y may be here, Y may be here. This Y2 will be the maximum value. Neutral axis will exactly be at center because it's a symmetrical figure. Neutral axis has to be at the CG. CG is at D by 2. So we have bending moment with us. We have neutral axis location with us. How the bending stress will vary. This is the neutral axis now. Neutral axis. At the center, this neutral axis is at D by 2. This is B dimension, the depth D. Okay. So I will be BD cube by 12 for the rectangular section. Y maximum value is going to be here. Y maximum will be equal to D by 2. This will be the maximum value of Y. So when we go to have a look at the bending stress, the variation of bending stress, this is the 0, 0 line. On one side of this line we draw the compressive stresses. On the other side of the line we draw tensile stresses. So since it is a cantilever, we know that this is going to be the tension zone, this is going to be the compression zone. Okay. So if in this equation I have got M bending moment with me, bending stress, I will find out tensile bending stress corresponding to this T by 2. Here both the values, that is this value is Y compressive, this value is Y tensile, both are equal to D by 2 because of the symmetry of the section. So if I calculate corresponding to YT, I will have sigma BT. Corresponding stress will be the bending stress in tension, which will be equal to M into Y. Y will be D by 2 divided by I is BD cube by 12. We have certain value, and this is tensile. Okay, this value will be sigma BT. Similarly, since Y is also same in compression zone also, we will calculate another value corresponding to YC. YC here is same as YT, and this value will be sigma BC. Now we join these. It will pass through 0 at the neutral axis. The stress has to be 0. This is compression zone, compressive maximum bending compressive stress. This is the maximum bending tensile stress. This diagram is the bending stress diagram. bending stress diagram. So the variation of bending stress is quite visible, that it is maximum at the outermost fiber. It will reduce linearly to 0 at the neutral axis. The sign will change. It will change from tension to compression or compression to tension, and the maximum value will again be at the other compression, at the other extreme fiber. This is the nature of bending stress diagram. But it becomes a bit complicated when the section is not symmetrical. If it is unsymmetrical, then we have to calculate the CG of the member and then calculate the bending stresses. Say for example, we have a simply supported beam now, again loaded with QDL, W per meter, span is L, okay, and we calculate the bending moment. For this particular beam, we know that bending moment will be maximum at center, and that will be equal to WL square by 8. So we have moment with us. Okay. The cross section of the beam happens to be an unsymmetrical section now. Say the section is an unsymmetrical I section. This is the unsymmetrical section. Top flange is not matching, is not similar to the bottom flange of the member, which makes it unsymmetrical. So the neutral axis has to be seen, or neutral axis has to be calculated, or the CG has to be calculated. It will not be at the center now. Somewhere here, this is the neutral axis. So initially, we'll have to find out, since it is compressive, since it is a simply supported beam, compression zone will be above the neutral axis, tension zone will be below the neutral axis. So we first of all calculate the CG, or what we say Y. If I calculate this Y from this particular level, from the bottom, this will be YT, and this will become YC. Okay, so we'll have to locate this neutral axis first. So we calculate this tensile YT as A1 Y1 plus A2 Y2 plus A3 Y3 divided by A1 plus A2 plus A3, where A1 is corresponding to this area, second triangle is this rectangle, and third rectangle is this one. So we correspondingly find out the CG, where the Y1, Y2, Y3 distances are up to the individual centers from the base, where from we have taken YT. This will be Y1, center of second rectangle will be Y2, and center of this from the base will be Y3. Okay, we'll find out the location of YT. Overall depth is D. From overall depth, we subtract YT and we obtain YC as well. Okay, we have got the location of neutral axis now. Now we have to see how we will draw the bending stress diagram. What will be the nature of bending stress diagram, variation of bending stress diagram. So our basic equation is M upon I is F upon Y, or bending stress sigma upon Y. Okay, Y we know now, Y is known, Y will be YC when we calculate stress at this fiber, Y will be YT when we calculate stress at the bottommost fiber. So Y is known to us, bending stress is to be calculated, I. M is also known to us, moment of inertia is to be calculated. Moment of inertia for all the three rectangles taken together, that will be BD cubed by 12 plus A1 H1 square, this will be for rectangle 1, plus BD cubed by 12 plus A2 H2 square, this will be for rectangle 2, plus BD cubed by 12 plus A3 H3 square, this will be for rectangle third. So all the three rectangles will have to take together, sum it up, we'll have area of A1, A2, A3 will be the area of rectangle 1, 2 and 3, and H1, H2, H3 will be the distance by which we are shifting the inertia. We are shifting here, Y1 will be this distance up to neutral axis from the CG of rectangle 1. This distance will be Y2, and here we are shifting by this amount, so this will be Y3. So we have got all the values. We will find out the bending stress. Sigma bending will corresponding to this compression. We will find out this will be equal to M upon I. We know we will have to multiply it by YC. So we'll get certain value here which will plot as sigma BC. Similarly, putting here sigma BT M upon I into YT in place of YC now, we will have another value of stress that will be sigma BT. Join this. This will pass through the zero level at neutral axis. Compression, tension, this is the bending stress diagram. So this is how we plot the bending stress diagram for various cases. So if we sum up, we find that bending stresses are developed because of the bending moment in the section. The resistance which the member will offer will be, the member will offer resistance to resist this bending moment, and that will be the bending stress in the particular member developed. This bending stress is either of compressive nature or sigma BT, which we call tensile nature. Okay, then depending upon the type of beam, if it is a cantilever beam, tension will be at the top, or if it is a simply supported beam, tension will be at the base. There is a certain pattern, that is the bending stress diagram we say. In bending stress diagram, it follows a certain pattern, okay, which we will have to analyze for. We analyze this bending stress variation corresponding to a bending equation. That bending equation we will have to remember. That bending equation we have seen is equal to M upon I is equal to sigma bending divided by Y, which is equal to E by R. From this particular portion, particularly from this one, we calculate bending stresses at various levels. For bending stress calculations, we need the type of the beam, load on the beam, which from that particular load and type we calculate this bending moment M. Inertia will depend upon the geometry of the particular member, and we have to locate the neutral axis. Neutral axis will be at the CG. So we'll have to locate the CG of the member, this CG. If it is a symmetrical beam, then CG will be at center. If it is an unsymmetrical beam, we will have to calculate this CG using our unit. After calculating the CG, we will have to determine the stresses at the top level, at the bottom level, and then we will have to draw the pattern of this bending stress, how the variation of bending stress takes place. So this is our scope in this particular topic. Thank you so much.